I hope everyone can. Will hope everyone can see my screen. Um, I guess we can get started. All right. Hello. Welcome to ACM AI's advanced track, everyone. If you're continuing here from beginner track, welcome back. And if this is your first time in an ACM AI workshop, hello, welcome. So so a few links on the screen right now. The anonymous feedback, which again was posted in chat, the attendance code for today, and the Discord. So the Discord link for ACM. So you should also have access to the slides. So shouldn't be a problem. So we can get started. Hi, I'm Adithya, and we also have, you guys introduce yourselves.
Hey everyone, I'm Sudhanshu, pronouns are he and him.
I'm Jenson. I'm a second year CS major. Pronouns are he and him.
Yep, and I'm Adithya, CS major as well, pronouns he and him, and we're all going to be helping out with advanced track this quarter. I'm going to pass it over to Vaishnavi as we begin to talk about our mission.
Hi everyone, my name is Vaishnavi. I'm the workshops director of AI this year. My pronouns are she, her. So in AI, which is a committee within ACM, which is the largest CS organization at UCLA, our mission is to build and develop a community of students at UCLA and beyond UCLA that are interested in AI and pursue this interest in AI. So we do this through 4 main initiatives. Our subcommittees. Next slide. Let me discuss our values first, actually. So our main value, one of our core values in ACM AI is to make sure that our members have some technical proficiency within machine learning. Like when you attend our events, we want you to be able to take away some skills that you can apply to other areas of your life, other projects that you're working on, and also just get a general idea of what AI is. In addition, we want to make sure that all our events promote a positive impact on society. And again, in the next slide, I'll talk about how we concretely achieve this. And we also focus on diversity and inclusion through everything that we do, from the events that we host, the people that we try to market our events to, and yeah, just in everything that we do, we try to make sure that we're catering to as wide an audience as possible and that we're being as inclusive as possible. Okay, finally, regarding the 4 subcommittees within ACMAI. So first off, we have workshops. You're attending a workshop event right now. Every quarter, we offer different workshop tracks. This quarter, we're offering beginner track, advanced and advanced plus plus. I'll be talking more about those on the next slide. But each of these workshops are a quarter long. They're weekly, around 2 hours long. And through these workshops, we hope to give you an idea of what machine learning is and just explore different topics. Often the topics we discuss are up to the members, like what you want to hear about. But like I said, I'll talk more about workshops on the next slide. In addition to workshops, we have 3 other subcommittees. One of them is events. So like I said, workshops are weekly events, but our event subcommittee hosts a lot of one-off events every quarter. In the past, we had an AI social impact panel where we discussed the social impact AI has and the importance of being conscious of how you go about working in the field of AI, because it does have a huge impact in our society and the way we approach AI, like, for example, like where we're getting our data from, like that's really important. And that's something that we discussed on our panel. We also had a research panel in the past where a lot of researchers at UCLA that work in the field of AI talked about their work, and members such as yourself attended and asked questions on how they can get involved, on what professors are researching. So if those are things that you're interested in, Events is hosting events like these all the time, and we post about these on our Facebook page, so be sure to check that out. We also have an outreach subcommittee, and the goal of outreach is to expand ACM AI's impact beyond UCLA, hence the name outreach. So what we do to achieve that is we teach machine learning workshops similar to the ones we teach at UCLA at local high schools. And outreach works really hard to develop content that high schoolers can easily understand and build from in the future too when they want to work on concrete projects. So if that's something you're interested in, definitely apply to be an outreach officer in the future. They do a lot of great work and they're really passionate about what they do, all our outreach officers. And then finally, we have our projects subcommittee, which is really important, especially members attending advanced track, which you're attending right now. Projects aims to give you like practical machine learning experience. In workshops, we try to incorporate as much like coding as possible, but a lot of it is theory. So if you want to work on like an actual concrete AI project and implement that and work on a real world problem, then projects is the way to go. And our workshops are structured in a way that if you attend, even if you have like very minimal machine learning experience, if you attend our beginner track and then our advanced track, you should be in good shape to apply to our project subcommittee. And I'll talk about exactly what projects is working on the next slide. So this quarter's project is very interesting, actually. So they're working on building an automated system that can detect what disease a cassava leaf has. And if you're not sure what a cassava leaf is, it's basically a very, very crucial crop in Africa. And often these crops are in danger due to like various diseases. So our project subcommittee is now aiming to build a system that if you take a picture of a cassava leaf, it'll automatically be able to detect what disease is affecting this leaf. And if you can find the source of your problem, it's that much easier to solve it. So that's essentially what they're working on right now. And if that's something that interests you, then feel free to reach out to our projects director, Harsh, or any of the officers. And it's awesome that you guys are in advanced track right now because you're on the perfect track to apply to projects in the future. So in the spring, I'm not sure if they'll stick with this project or if they'll start on a new project, but regardless, definitely reach out. Okay, and finally, these are the workshop tracks that we're offering this quarter. Since you guys are here for advanced track, I'm assuming that you're already familiar with beginner track material, but if at any point you want to review what linear regression is, logistic regression is, feel free to drop by. Beginner track workshops are Tuesday, 7 to 9. Advanced track, the one you're attending right now, will be Thursday, 7 to 9 every week. And in this track, Sudhanshu, Jenson, and Adithya are going to go deeper into exactly what we're exploring, but it basically picks up right where beginner track left off. We're going to explore what neural networks are and just discuss different models, both the theory behind them and implement these models. Advanced Plus Plus is also happening this quarter, and this is a new track that we haven't offered in the fall. But basically what Advanced Plus Plus is we structure the workshop a little differently in that instead of having to attend all prior workshops to be able to attend that week's workshop, each week is independent. So if there's a specific topic you're interested in, for example, this week, the Advanced Plus Plus track officers talked about transformers. At their next workshop, they're most likely going to be talking about fair ML. So these are topics that you're interested in, even if you're still in like advanced track right now, feel free to attend Advanced Plus Plus track workshop. In fact, like I encourage you to do so because each week's topics are completely different. So you don't need to have gone to all the prior ones to attend an Advanced Plus Plus workshop. So those are Mondays 6 to 8. And all this information is on our Facebook page, so feel free to check that out. Feel free to reach out to me in the chat if you have any other questions, but I've been talking for a while. I'm going to hand it off to Adithya so we can get started with today's workshop.
All right, cool. Thanks, Vaishnavi. A lot of stuff going on in ACM AI, so feel free to reach out if you guys want to know more. All right, let's begin with a quick look at some logistics. Let's overview of what you guys can be expecting to do this quarter. So here's a tentative schedule. 8 weeks. We're going to be covering a whole bunch of things, as you can see. And we also have in the last 2 weeks of the quarter, week 7, our week 7, in reality, it's going to be week 9 and week 10. We have guided projects where you're actually going to be applying the theories you learn during weeks 1 through 5. It'll give you a good chance to like really understand how neural networks and all that stuff works in reality. And of course, Thursday, 7-9 PDT, I'm gonna stick with this time. So yeah, let's move on. Here's expect prior knowledge. Obviously some comfort with coding. We'll be using Python in this track. So brush up on your Python skills if you haven't in a while. Basic machine learning knowledge as well. Your knowledge, if you attended beginner track, that knowledge is more than enough. Linear regression, logistic regression, all that type of stuff. And of course, basic knowledge of working with data, because ML is all about data. All right, cool. Here's what we're going to be covering today. Taking a review of machine learning, as well as taking a look back at linear and logistic regression, as well as a quick introduction to neural networks. So let's get into it. Any questions? Feel free to like unmute or put it in chat, whatever, it's all good. All righty. There are no questions. Let's begin. We can start off with a quick review of linear and logistic regression. So, again, machine learning. What is machine learning? So, machine learning obviously teaches the computer how to answer questions that we don't want to. So in traditional programming, you obviously have to design a program, and you have data to pass into the program, and your computer executes some instructions to give you the output that you want. When we look at machine learning, things get flipped. So you have the data, and you might have output. Oftentimes, it's labeled output, and you feed these into a computer, and it spits back, and the computer spits back a program. A machine learning model that you can use to apply to data that the model has never seen before and get the expected output that you would want. So yeah. So we have 3 different types of learning in the machine learning. We have supervised, unsupervised, and reinforcement learning. Supervised learning is when your output data is labeled. So that means predictions from the model are compared to the expected output from the labeled data. And this helps for direct feedback to the model if it's on the right track. And the models that we learned in beginner track, logistic, and linear regression were examples of supervised learning. In unsupervised learning, that's when the model is given no guidance. So that means there are no labels for the output data, and the model needs to pick up on hidden patterns on its own. So one example of this is clustering. You might have data points that might end up clustering on an n-dimensional space, and that's when unsupervised learning comes in, because then the unsupervised learning can identify those different clusters and pick up on that hidden structures within the data set. Yeah. And of course, we have reinforcement learning, and that's when we reward the model for making the right quote-unquote decisions. So eventually the model will learn how to do a series of steps, series of actions to get the required output. In advanced track, again, we're going to be looking primarily at supervised learning. So yeah. All right, we're going to go through a few key elements of machine learning. First off is representation. It's important to be able to represent knowledge, or data. On the screen right now, you can see an example of decision trees. This is how a model known as random forests work. We're not going to be covering that in advanced track, but it's just an example how we can sort of represent knowledge and data and kind of figure out what's going on visually. And then you have evaluation. So evaluation tells us how good of a job our model is doing. So there are many different ways to calculate evaluation. There's cost, there's margin. Cost is also known as loss. And we have margin, entropy, the mean squared error. All of these gives us an idea of how well our model is doing. And right here in the example, you can see a confusion matrix. And again, this gives us some key important values, precision and recall. We'll be using this. We'll be defining these terms later in the workshop series. But yeah, you'll be working with, you'll be trying to evaluate your model a lot to kind of understand if it's on the right track and whether there needs to be some rethinking when you're designing the model. So yeah. And we have optimization. So AI and ML can really help us optimize very computationally intensive algorithms. So right now, once again, in this example, I believe it's the traveling salesman problem. Again, which is a very computationally intensive, you need a very computationally intensive algorithm to solve the traveling salesman problem. And that's where ML can really help us optimize. So yeah, those are some of the key elements of machine learning. We'll also take a look at classification versus regression. So these are like the two biggest like subfields within machine learning. So classification, the main goal of classification is to take some set of input and decide and group them into a certain number of discrete groups, classes, whatever you want to call them. So as you can see in this example, we have a hand-drawn digit that we pass into a classification model. In this case, neural network, and the model ends up spitting out the probabilities that it thinks that digit could be 0 to 9. So this is it's known as classification because we have certain distinct groups. There's no continuous output. The output here is discrete. And of course, the probability for thinking that the digit is 9 is higher than the ones thinking it's a 0 or a 1 or any other digit if our model is working as expected. And then we have regression. Regression deals with continuous outputs. So that one example of that is linear regression. And that can be used when we're predicting house prices. So we might pass in different key features of a house to our linear regression model. Those features could be the square footage of the house, the number of rooms it has, its location, all that sort of stuff. We pass it into the model, and the model spits out a continuous, an output on a continuous space. And as you can see in this case, we're seeing 198,000, but the output can be continuous. It can be any value on the real number line. So yeah, those are the two biggest differences between classification and regression. I'll pass it on to Sudhanshu right now to take over. So yeah.
Cool. So can everyone see my screen?
Yeah.
Awesome. So like Adithya mentioned, we're gonna do a quick review of linear and logistic regression because a lot of the terms that we use here are kind of become part of our vocabulary later on in the workshop series. So, and also what we're gonna find out is that even though linear regression and logistic regression are really, really simple, they kind of form the building blocks of all this other really cool stuff like neural networks and deep learning. And we're gonna go through this relatively quickly because we wanna save some time for the neural network stuff that you guys probably came for. So to start off, what is linear regression? So in a linear regression problem, we're given a bunch of data. So all these green points over here, and our objective is to find the line of best fit, this red line over here. What does that mean? It means we want to find the line that best models, that best represents all of this data. And once we have this line, we can use it to predict the output of inputs we've never seen before. So we say the value 4.5 has never been seen before. I check what my model outputs and I get a brand new value. And like Adithya mentioned before, the outputs are continuous. So they can take any real value between negative infinity and infinity. And that's what makes it a regression problem. So in a linear regression model, we have this linear function over here. And the way you read this is y hat is equal to b plus wx. So let's for a second ignore all these later terms. If you just look at this first term, second term, and the third term, you have y is equal to wx plus b. And that should look pretty familiar because that's just the equation of a straight line. And the way you extrapolate that to higher dimensions is by just adding a bunch of other x's with quote unquote slope terms right in front. And that's what a linear regression model in n dimensions looks like. So instead of a single value x, we have a vector x. We have a quote unquote slope vector, which we prefer calling a weight vector w. And we have a bias, which is a real number, which is analogous to the intercept. And once we have our model, we need to try and figure out how well it's performing. We need a way to evaluate it and tell us how close we are to the true solution. And that's what we need a cost function for, or a loss function, or an error function, or any other name. And the function that we most often use is something called mean squared error. It's a really good function for linear regression problems. And this is something you should probably have seen before. It simply takes the predicted value, y hat, the true values, y, calculates the distance between them, and averages it out. So the function is called mean squared error. We have a mean, we have a squared, and we have the error. That's pretty much how I remember it as well. And that tells us how well our model is performing. The lower it is, the better our model is performing. Now, once we have our model, once we have our cost function, we need to try and minimize the cost function somehow. And the way we do that is using an optimization algorithm. The algorithm that we most commonly use, or the easiest to understand, is gradient descent. Now, let's see how gradient descent works. Our objective is to minimize this loss. And if we think about it, the loss is a function of y hat. Sorry, give me 1 second. Yeah, the loss is a function of this y hat over here. In turn, y hat is a function of w, b, and x. So if you really think about it, the loss is a function of w, b, and x. You just pass it through through the y hat and take it back to w, b, and x. So to minimize our loss, what we need to do is find the best possible b and w. X is fixed, we can't do anything about that. So we need to find the best possible b and w. And that's what gradient descent helps us do. This term that we calculate over here is the partial derivative, or the gradient. And formula aside, nobody cares about the formula right now. What we do is we take the old weight and we subtract the gradient. That's what gradient descent means. So we take the old weight, subtract the partial derivative scaled by some learning rate alpha. And our model over successive iterations converges down to this minimum. So we take our old weight, we keep subtracting, and eventually converge. Okay. So let me pause here. Again, I know I went really quickly, but we want to save time for neural networks. Does anyone have any questions about anything I just covered?
I have a question. So really quickly, could you go over how the error function affects the gradient?
Okay, sure. Give me a sec. So the way we calculate the gradient is it's the gradient of the error function. So this del L, the L is the error function or the loss function. So what we do is we calculate how much does the weight affect the error, and that's how the error function comes in here. Does that help?
Yeah, thanks.
Cool. Okay, I think there's a question in the chat. Hopefully that was answered. Is there any other questions? Okay, let me press on. Okay, so let's do a quick check your understanding poll over here. Oops, my bad. Yeah, so we'll just do a quick poll over here just to make sure everyone's on the same page. Just answer these three questions over here. And they're pretty simple stuff. Hopefully everyone gets them. Okay. Okay, about halfway done. Okay, gonna give it like 10 more seconds, just so everyone has a chance. Okay, okay, let's end it here. Cool. Let me share the results. And yeah, everyone got the third question right, which is awesome to see. Gradient descent does minimize the cost function. The output of linear regression is actually continuous. I see a few people here and there. Yeah, so we had a multiple choice question. I think I probably threw some people off. It's continuous and a real number, but well done, whoever answered either of them. And the first question, a little bit of confusion, but yeah, it's data plus output is equal to program. So what we're doing is we're showing the model some data and we're getting a program or a model out of it. Okay, so let me stop sharing this. Cool. So now let's talk about classification models, which is the other thing that Adithya mentioned. And a classification problem is essentially one in which you need to categorize data into 2 or more classes. So positive or negative, yes or no, true or false, 0 and 1, whatever you want to call it. And that's what a classification problem is meant for. And the way we usually do classification is using a logistic regression model. Now, this is very, very similar to linear regression. Like the name is similar, so I should give you a clue. And the linear regression model has a function y is equal to wx plus b. So the logistic regression model simply takes this output and applies what we call an activation function to it. Now the activation function is just some non-linear function. In the case of binary classification, where we have only 2 classes, we often use a sigmoid function. There are other functions as well, but for a second, let's consider the sigmoid function. It's this function displayed over here on the side. What it does is it takes this straight line, which was produced by linear regression, and well, makes it curved. So as you can see, it very nicely separates the plane into these 2 regions, greater than 0.5 and lesser than 0.5. And that's what helps us perform classification. When we do multi-class classification, we often use a softmax function. And that's something we're going to be using in this workshop series as well. It's just a generalization of the sigmoid function to more classes. And activation functions, like I mentioned, just add some non-linearity to the model. It takes that straight line and makes it curved. That's the best way to think about it. And there are other activation functions that you can explore as well, like ReLU or TANH. And sigmoid is just a very intuitive function to get started with. Okay, so let me pause here again for a second. Does anyone have any questions about logistic regression? Okay, I think we're good. So what we've done here is actually implemented linear and logistic regression using Python. And the reason we did this is A, for completeness, and B, to kind of show you all how simple it is to implement these models in Python. Because as you can see here, it takes 6 lines of code to implement the entire model, which is pretty awesome. And I'm going to walk through this line by line. The first thing we do is we've imported this library called sklearn. It's called scikit-learn, and it's meant for these kind of machine learning tasks. We import the linear regression model because that's our task. And the next thing we do is we get this function known as train test split. What that does is it takes our data and it splits it into a training set and a testing set. Here we have specified that the testing set size is 20% of the total data. Then we construct our model. We've called it reg. We simply say linear regression fit the training data, and that's it. So this function reg is our entire linear regression model. All the other stuff we talked about, the loss, the training, gradient descent, all that stuff happens in this one line of code. Once that's done, we can use it to test our model out. So we find out what the score is, we can predict new values, whatever you want. So in the 6 lines of code, you can implement the entire linear regression model. Similarly, for logistic regression, we import the logistic regression model. We perform our training and testing once more. We perform our fitting once more. We perform the score. We do the scoring once more. We do the prediction once more. So it's almost the exact same workflow. And in fact, these are only a couple of models in the sklearn library. If you try something else, let's say KNNs, it is literally going to be something like replacing this with KNNs, replacing this with KNNs. We still fit it. We still do the scoring, still do the predictions. So sklearn is a very, very versatile library, and it has this really nice template with which you can do all these nice tasks. Okay, so let me pause here again for any questions about the code. What is a random state? Okay, it's a good question. So for everyone wondering, there's an argument over here called random state. And what that essentially does, okay, so let me put it this way. Training and testing not only splits your data into 80-20, what it also does is it shuffles it around. So let's say we had 100 points, all those points get shuffled around in some random fashion. And if we set the random state in the beginning, and we always call it with random state 5, it'll shuffle it in exactly the same way. And of course, this is an arbitrary choice. We can call it random state 2409, and it'll work just as well. And it's just to, if you're doing it successive, if you're running the program multiple times, it'll give you the same output every single time. So yeah, I hope that helps. Any other questions? Yeah, like I mentioned, it's like a seed to a random number generator. Okay. Let's do one more check your understanding poll. Again, just to make sure that we're all on the same page here. Okay. So you should see the poll on your screen now, I hope. Okay, yeah, there we go. Okay, we're getting there. Few more seconds. Okay, let me end the polling. Share the results. Okay, so a lot of you got the correct answers. Indeed, the best the problem in which you pick a regression model is probably problem number A, predicting the amount of rainfall, because that's kind of a continuous thing. Is it 5 inches? Is it 100 inches of rainfall? And the output of a classification model, we understand a little bit of ambiguity here. The answer that we're looking for is discrete, because at the final output, in the end, you can make some kind of prediction, and that's a discrete value. So that's why we worded it this way. But numbers between 0 and 1 is definitely a reasonable answer as well. It's kind of the probability of a prediction. So well done, everyone. So now, to the stuff that we've all been waiting for, we're going to do neural networks. So I'm going to hand it over to Jenson.
Wait, can you stop? Okay, I'm just gonna override you. Okay. All right, can you guys see my screen? Okay, cool. So let's do a brief introduction to neural networks. So most of you have probably heard about the term neural networks before, just because it's one of those machine learning buzzwords that gets used a lot in recent years. So what exactly is a neural network? So let's get a better idea of what a neural network is by looking at this diagram here that kind of represents the structure of a vanilla neural network. So the circles that you see here represent neurons, except for maybe the input layer, because those are technically just input values or features of your model. And the arrows that you see here represents the connections between neurons in different layers. So as you can see, a neural network can have multiple layers, and each layer can have multiple neurons. And so this is kind of why this whole structure is called a neural network. So as the name suggests, a neural network, at least at a very high level, is inspired by how the human brain works. So to get a deeper understanding of a neural network, let's first take a look at an artificial neuron. So does anyone want to take a guess at what an artificial neuron is? Feel free to type in the chat or unmute yourself. I'm gonna wait for maybe like 30 seconds. All right, so an artificial neuron is actually a mathematical function that is intended to model, I guess, the behavior of a biological neuron, at least in a very general sense. So an artificial neuron consists of a set of inputs represented by the input vector x, a set of weights that is associated with the connections between this particular neuron and all the neurons in the previous layer, and as well as an activation function g that pretty much activates the neuron once the weighted sum of its input is above a certain threshold. So to compute the output of this neuron, we first take the weighted sum of its input and add a bias term to it, and then feed this whole thing into an activation function g, and that would give us our output y. So recall this is actually exactly the same equation that we use for logistic regression. So this is kind of why we wanted to review logistic regression earlier in the workshop. All right, so any questions regarding to the structure of a neural network or artificial neuron? I'm gonna pause for just a moment. Okay, cool. So, oh wait, there's something in the chat. Can neurons output values outside of 0 and 1? Okay, that's a good question. So that actually depends on your activation function. So for example, if you use sigmoid as your activation function, like we did for logistic regression, then the output of the neuron would be between 0 and 1. But if you use another activation like ReLU, then yeah, it can output all positive values and as well as 0. If you use hyperbolic tangent as another example, then it would output values between -1 and 1. Would a linear model work too? Wait, oh, without an activation function? But I'm not sure what that question means. Like, I guess it depends on the problem that you're trying to solve. So as we'll get into this later on, like neural network can solve problems that are more complex. Okay, who do know which activation function to use? Okay, wait, do you mean how do you know? Okay, I guess you can actually, for a neural network at least, you can, what tends to happen is you use different activation functions for different layers, but yeah, we'll get into that like later. Okay, cool. So, all right, so you can actually also think of a logistic regression as a perceptron, but they're not completely the same thing. Like if you Google the differences between a perceptron and a logistic regression model, you will find some subtle differences between the two. But at least for our purposes, we're just gonna consider these two models to be the same thing. So on the right, you can see a diagram representing a single layer neural network. So to build this neural network with one hidden layer, we can actually combine two perceptrons together by feeding the output of one perceptron as an input to the next perceptron. And so this is also why neural networks are sometimes called multi-layer perceptrons, because one layer of this neural network kind of represents a perceptron. Oh yeah, okay. So the neurons in the hidden layers are sigmoid neurons. So that's the activation function of choice here. Okay, so at this point, you might be wondering, so why bother with all of this? So in other words, like what makes neural networks better than something, say, like a logistic regression model? So the simple answer to that is neural networks allows us to model more complex data. So in more formal terms, a neural network has a greater representational power than a logistic regression model or any other linear classifiers. So because neural network has multiple layers, this essentially allows us to introduce more nonlinearity into the network, which would allow us to do a better job at modeling nonlinear data or nonlinear relationships that are pretty common in real world data sets. All right, so I know that could be a lot to take in at first, but for the next workshops, we're gonna dive a lot deeper into neural networks. I'm gonna check chat real quick. Okay. What is the difference between a neuron and a perceptron? So a neuron is just like one node in the neural network, and a perceptron is see if I can go back. Oh wait, I have the chat opened up. Wait, give me a sec. Okay, so a perceptron is this entire model. sorry if I wasn't clear about that. So a neuron is just one node here, and the perceptron is this entire model of one layer, which I talked about is the kind of similar to a logistic regression model that we've been discussing, but it's not completely the same. Okay. So yeah, for next workshop, we're gonna go a lot deeper into neural networks. So first, we're gonna define the architecture again, and we're gonna walk you through the feed-forward pass through our network, and then we're gonna define the loss function that we're gonna use. After that, we're gonna perform gradient descent to adjust the weights of our network, and last but not least, we're gonna back propagate the errors through the network. All right, so any more questions?
I have a question.
Go ahead.
So I guess you talked about we can use gradient descent to adjust the actual values of the weights between each neurons. But how do we decide which neurons affect the next neurons, like the neurons in the next layer? Because it looked like in the diagram that not all neurons like connected to each other between layers.
Okay, so that's a good question. Okay, sorry. Some technical difficulties. So in the single layer neural network here, so each neuron in one layer is connected to every neuron in the previous layer. So as you can see, this purple neuron here is connected to the blue neuron here, the second blue neuron here, the third blue neuron here, and the last blue neuron here. So this is called a dense neural network because every neuron in the layer is connected to every neuron in I guess the next layer and the previous layer. So, but this is not necessarily the case for other architectures, as you'll see later in the series when we talk about convolutional neural networks. But yeah, neurons are not connected to neurons in the same layer. So this neuron is not connected to this neuron, if that makes sense.
Okay, that does make sense. Yeah, so I guess also like if a given neuron didn't need information about a neuron from the last iteration, like the weight could just go to 0 too.
Yes,
that would
that
be
is correct.
I guess like a follow-up question is, how do we decide how many layers there are or how many neurons there are in each layer?
Okay, that's an excellent question. So I guess the number of neurons in each layer and the number of layers in your neural network is what's called a hyperparameter. So you wouldn't be able to figure that out just by using like a training data set. So what usually happens is you have like a separate validation data set that is unique from your training data set and testing data set. So what you do with the validation data sets is you basically, I guess, test the validation data sets on like different values of like, there's some different architectures with different number of neurons and in each layer and different number of layers. And then you just see how well they do on the validation data set. So what usually happens is you pick the best value of those hyperparameters on the validation data set, and then you just proceed to test the accuracy on your test data set. Does that make sense?
So it's like basically something you determine heuristically? Or do you actually have like some kind of formal algorithm to determine that?
Yeah, I guess it's more heuristic, but like, I guess with like a validation data set, I guess you can't think of it as like hyperparameter tuning as like an algorithm, but it's more or less just, I guess, brute force, just because I mean, you can rule out some like values, like this single layer neural network's probably too simple for, I guess, most applications. So you can rule this out, but like you would have a range of values that you have to test on your validation data sets. And that's usually brute force. Or you can just, yeah, so it's empirical.
On slide 36, which is one slide before the one you're displaying right now, like the neurons are labeled like number, color, number, shape, number, smell, and then the output says number, type of fruit. So I guess like
Yes.
in that sense, it does make sense that it would have to be something like you design, because like you can't classify those like.
Oh, those are
you
just
know.
the inputs. So those are just features of your data sets. This is just
Okay,
like, yeah. So this is like a perceptron. So this only has like, there's no hidden layer. So the input layer is kind of just features of your data set. So the order doesn't matter if that's what you're asking, because
Oh yeah,
if
never
you
mind.
flip
I
the
just
order,
misunderstood what this all meant,
okay, that's
but I
totally
think I
fine.
get it now.
All right. Okay, so where was I? Oh, questions. All right, is there any other questions? Okay. I'm gonna briefly talk about upcoming events. So the main one is the workshop next week, where we'll be continuing with neural network and fleshing out their structure and implementation. And also we're gonna go into a lot of detail about the backpropagation, which is the basis of almost all deep learning. I guess not necessarily machine learning, because there are like a lot of other models that does not require backpropagation, but for deep learning, yeah, I think every model in deep learning is relying on, heavily dependent on backpropagation. So that's really exciting. All right, so thank you all for coming, especially for those who also came to our beginner track. So feel free to fill out our feedback form, as well as following us on Facebook, and check out our GitHub repository for Advanced Winter 2021. Okay.
Thank you.
I thought we have another question. Okay, see you guys.
Thanks a lot.
All right, thanks for coming out, guys.
Yeah, really appreciating you guys being here.